One. Here we go, exercise 9D. We're going back to 9D because after you learnt all the derivative rules, hopefully you're now a bit more familiar what the derivative is. It's to find the gradient. Now you're visualizing it. So here, the answers for each one. Let's have a look. A already did. Derivative of linear is a constant, or if you just analyze the graph, the gradient is consistent at 1. Should have got 1. The other one for B should be -1. Hands up if you got -1. Constant horizontal line. Beautiful, good. So it should be -1 like that because it's a negative gradient. It's consistent. Let's have a look at next one. C. I've already put all the signs there for you. So on the left side, you can see the gradient's all positive. Obviously, it increases and then it decreases over time. So that means it's high and then it gets lower and lower and lower. By the time it reaches this point, it should be 0. So it should have an x-intercept where that peak is. And similarly with the minimum over here, there should be an intercept at 1 as well. Hands up if you got the quadratic equation there. So it should be 1 and -1 on your x-axis. Good, labeled, very good. Let's go to D. Notice D tells you that that is a point of 0 gradient. So that's a hint that that means your derivative graph must intercept x equals 0. It's a cubic. So likely you can predict it to be a quadratic graph, or you can analyze its positive. Hands up if you got D correct. All right, so far so good. E was slightly different in the sense that it didn't have a 0 gradient. You can't assume. So hence it doesn't touch the x-axis. So it should be a quadratic as well, but doesn't touch the x-axis. Hands up if you got that correct. Okay, cool. I thought that would have tricked a few. And then your last one. That's a quadratic, clearly a turning point at the center there at 0, 2. So I expect it to be a linear equation. Derivative of x squared is a linear equation. It's positive as well. So negative first before positive gradient. Linear and intercept at 0. Hands up if you got all 6 correct. All right, really good. That's 9D pretty much. That's what you're practicing 9D. Try the second one if you haven't done so. What about sketch the graph of? Now, we used to teach this function. I think maybe only special kids know it. What's this function called? Anyone know? Hands up. Pat?
Absolute value.
Absolute or modulus function. And it just looks like this, if you ever see it. Has 2 vertical lines. Okay, and it just basically means whatever x is always going to be positive. That's what it's trying to say. Okay, so normally, for example, a y equals x line would look something like this, right? Because x is always going to give you a positive value, even when x is -1, it treats it as if it's a positive 1. So it actually mirrors whatever you have at x equals 1, so that's why it then looks like that sharp V point. This was special graph because when you have a V shape, unlike a quadratic shape, this point here is not a 0 gradient. You'll learn that in the next lesson where we talk about differentiability and continuity. That's what we're doing next. Okay? But that does not have a 0 gradient there. So if I asked you to sketch the derivative graph, it means that there is not going to touch that 0 point. Have a go with this one. What would the derivative graph of this look like? Let's give you answers. Did you get, on the left side, it's clearly a positive gradient. Rise is 2. Run is 1. So you should have a gradient of 2, positive 2. So it should be a nice horizontal line at 2. And then the other side is a nice horizontal line, but it's a negative gradient. So it should be at -2. Now you're going to be careful here. If you got the 2 lines, that's good. The other mark comes from the endpoints. I told you before there is not a 0 gradient. I'll explain it in the next lesson about differentiability. So that means you cannot include at x equals 0. That means you have to put an open circle at this point. An open circle here because when x equals 0, you do not have a derivative. That's what I wrote here. Cannot equal to 0. The derivative does not equal to 0 there. Okay, so delta y, delta x does not equal to 0 at that point. Okay, in fact, it just doesn't exist. Hands up if you had the open circle. Oh, wow. Okay, you guys must have learned this beforehand. Otherwise, another way to help you understand or memorize that, the gradient, as you can see, if I'm moving from the right-hand side, so from infinity down to 0, it's clearly approaching a gradient of -2. Whereas from the left-hand side, from negative infinity close to x equals 0, the gradient's approaching 2. So right at x equals to 0, is it positive or -2? We don't know, hence it's undefined. Okay, so it's not the same. Whereas a quadratic, you can actually see it curves closer towards 0. That's why you can say that the gradient is 0 at that point. Yep.
Limits there, or is it just really like?
It is limits.
Okay, so
Yeah.
Even then, limit,
Yeah.
Because you're telling to come from the left, you would run another whole line.
Yeah.
yeah.
That's essentially me describing limits, but not using limits. All right. Here's a few notes for inflection points. You guys may have learnt this from Spesh, but if you haven't, then this is a nice thing to know. Just a couple of words or terminologies for you to understand here. Inflection points. Thanks, team. Focusing. Next page, inflection point notes. So an inflection point is where a curve changes from concave upwards to concave downwards or vice versa, right? What is concave upwards and what is concave downwards? You can kind of think of it as concave is caving in. So you can see here, that's caving upwards, or you can think of it as convex downwards. Convex is like how much out. So you can see it's going downwards. The idea is that concave upwards is when the derivative or the gradient or the slope is increasing. So if it looks like the slope is increasing is when it gets steeper. Yeah? If it's increasing, we call that concave upwards. So you can see it's sort of increasing from here. It's increasing, 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 but in the negative direction. Yeah? Whereas concave downwards, you can see it's the other way around. It's the derivative gradient or slope is decreasing, or you can think of it as aka convex upwards. So the moment the inflection point is actually the point at which these two changes. So if you think about a typical cubic graph, this is what a cubic graph kind of looks like. Can you see there's two components there? There's this component, and then there's this component. One is a concave upwards, and one is a concave downwards. So here's your concave downwards, and then it changes to concave upwards. So the moment that it changes, that's the definition for your inflection point. Okay, so that's pretty much what that's trying to say there. Okay. Now, there is a quick way to find your inflection point, which is what I said in the Spesh here. I've got a picture here just to help you visualize that concavity. See how one is concave down and then there's concave upwards. Somewhere between these points, the rate of your gradient changes. So it's like, it's slow, 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 and then at some point, it starts to increase. Yeah? So an increase, 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 and then a decrease, and then increases again, right? But that point where it changes from concavity downwards to upwards, that's where your inflection point is. But what they're really saying there is, it's when the derivative, which is the rate of change, is its fastest point, or maximum point, the turning point of it. Yeah.
Like on a sine graph, that'd be on every time it intersects the x-axis. It's kind of increasing until it hits the x-axis, and then it's decreasing.
For the derivative graph or the
inflection point of the every point along the x-axis, right?
Of the derivative graph?
No. Of the actual graph, but when you have the derivative, then of the derivative graph, the inflection points up along where the previous graphs intersect with the x-axis.
Oh, I'm just trying to think of an example that might not be true. Not necessarily all the time,
Okay.
but I see what you're trying to say. It's essentially, yeah, it's when that moment where, yeah, I don't even know how to, yeah, it's when there's a change that I can see in the graph when it's concave to concave upwards. And it not necessarily means it's the x-intercept, but it can be. It can be, because I can see what you're trying to say.
Sine plus 1, then it'll be along, 1. Or sine x plus 1. And then it'll be along, like, every time it passes over 1.
Yeah.
Yeah.
I'll come have a look and explore that with you later,
Okay.
just to see. Now, the other way is that you can do what the special students would do. It is the double derivative. It means that in your derivative graph, where it's the maximum or minimum, that's when an inflection point occurs. So here, when you find the derivative, you're finding the gradient of a function. We can quickly find out the function is concave upwards or concave downwards by finding the second derivative. Because the second derivative talks about the rate of your gradient. Yeah? So, when you do the second derivative and it's positive, you're asking what is the rate of your gradient? If the rate of a gradient is positive, it means it's increasing. But if it's increasing, then it's concave upwards. Okay? So that's, if you look at the graph again, this is what I mean by the derivative of gradient slope is increasing. So if you did the double derivative, you then learn at that particular point, is the rate of your gradient, is it going up or is it going down? Okay, so if it's increasing, it's positive. If the rate of the gradient is decreasing, then it is concave downwards. Yeah? So here, second derivative, if it's negative, so the rate, think of the speed of your, think of it as like the acceleration of your speed. Yep. And I've expanded it for you, so it's x cubed minus 6x squared plus 11x minus 6. Find the first derivative, find the second derivative, and then I want you to find if it has an inflection point. We would then need to find what? The second derivative, which is either maximum or minimum, is equal to where the 0 point is. Because where it's 0, that's where it's at maximum point. Everywhere between is either concave upwards or concave downwards. Okay? So you either got concave upwards, downwards and upwards. And then at that point, this must be when it's 0, because one has to be a double derivative that's negative, and one is a double derivative that's positive. Then there has to be a point where it changes. That moment where the double derivative changes its sign is what we're talking about where the inflection point is. Okay, so I'll say that again. The moment the double derivative or sign of the double derivative changes from negative to positive or vice versa, that is where the inflection point is. That's essentially what this page is meant to try to teach you. Okay, to get you to understand, it's about that double derivative. It's the rate of change of your gradient. And we know that if it's positive, it means that the rate of change is increasing. If it's negative, it means the rate of change is decreasing. And you'll see that as you're finding the double derivatives for this graph, you'll understand that there's the concave and the concave downwards and upwards. The moment it changes is where we call our inflection point. Okay, and then we can shortcut that by letting it equal to 0. But it does mean you have to check if it's concave left, downwards, and then negative and positive on the other end. Okay. All right, I'm going to pause the video there.